Hi everyone, welcome to Weekend Upscaling. Today in this video, we'll be looking at the system design of TinyURL. Some of the famous websites which provide this TinyURL services are TinyURL in itself, Bitly, Rebandly, etc. And also, if you look at your Amazon website, when you try to click on share a particular product, um, instead of sharing the longer version of the URL, a short URL would be generated, which will be short and handy to share it across. If you look at this page over here, let me take the highlighter. Yeah, over here for this given long URL of some GitHub page, the system would have generated a very short URL, which is of like the website and domain and 7 8 characters. Yeah. Let's move on to look at the functional requirement. When a user provides a long URL, our system should be able to generate a short URL for the given long URL and also store that short URL in the DB. So why do we store the short URL in the DB in this case? Is because whenever the shared URL or the receiver comes back with the short URL, our system should be able to respond back with the long URL or redirect the user to the long URL or long URL and navigate to that particular website, original website. Like we have two functionalities. One is create, another one is get. Moving on, here I have listed down some of the optional requirement. If you feel like you want to skip the optional requirement, please feel free to skip the optional requirement. The very first requirement over here would be to store the number of user clicks. Say suppose this particular URL has been clicked 100 number of times or 1000 times, we should be able to capture the total number of clicks for the given short URL. That's the optional requirement number one. And we also should be storing the created by who created the short URL, created time, and if we have an expiration policy, we should store the expiration time after which the URL can be deleted from our systems. And how to and the option and the last thing in the optional requirement would be to delete the expired offers. Yeah. The scale of the application. I have divided this into two subcategories: scale of writes and reads. Assuming at any given point in time per second, we have 250 unique users who are trying to create short URLs using our website or using our system. Then, for every 250 every second, 250 URLs will be generated, which will be multiplied by 60 seconds for every minute and 60 minutes for every hour, and following that we will be multiplying it into 24, 250 into seconds, which is 60, and into minutes, which is 60 again, and into 24 hours per day and 365 days. When we multiply this, we would be generating somewhere around 15 to 16 billion writes per year. So this is the capacity of the system. So basically, around 15 billion writes would be happening into our DB. Given that in mind, let us move on to the application scale of rate. To keep it straightforward, fair and simple, let us assume the read to write ratio is 10 is to 1. So there are 10 reads for every writes that is happening into our system. So basically 15 billion writes into 10. We'll have somewhere around 150 billion reads per year. Moving on to the next topic in our capacity planning would be to determine the length of the short URL. How much characters we can, how much minimal characters we can fit into the short URL to be able to support this scale of system. There are two approaches ideally. The approach one would be generating 10 numbers 0 to 9 and 26 alphabets A to Z, um, ignoring the case sensitivity. So in this case, in total, we'll have 36 possible combinations per character. So when we look into the calculation, when we have 8 characters, our system should be able to support 2.8 trillion short URLs. 36 to the power of 8 will be 2.8 trillion. And the second way to do is, we can in the second approach we can reduce one more character, like by introducing case sensitivity. So suppose we'll taking like all 10 numbers from 0 to 9, and A to Z, all small letters, and the capital letters from A to Z. So 10 plus 26 plus 26, which will be somewhere around, which is like the 62 characters per 62 combinations in a given character. When we take the 62 to power 7, we'll be looking at somewhere around 3.5 trillion. At an estimated rate of like 15 billion URLs per year, our system should be able to easily support 300 billion URLs when we have base 62. Hmm. And seven characters should be more than sufficient for this. Provided that like we implement an expiration policy and rotate some of the short URLs, then we should be good uh, for this scale, uh, with or without expiration. So moving on, the next section would be the memory estimations, which is the total memory needed by our database. Assuming like we have one, two, three, four, five columns in our mandatory table where the short and long URLs are stored. Short URL would be of size 7 bytes per row, and we can take it as a character type. And the long URL would be a varchar. We can store it as a varchar, and let us assume that like it is 100 bytes on an average per row. And created by, we can store as an UUID, which will be 16 bytes per row. Expiry would be 4 bytes, and this can be an epoch, Unix timestamp. And created time, let us store it as a timestamp, and this would be 8 bytes per row. So the short URL over here, when it has 7 bytes per row, when we multiply it into 300 billion rows for a 20-year period, we might end up having 2.1 TB in short URL column. And similarly, we'll have 30 TB of data required for long URL, and 4.8 TB of data required for created, and 1.2 TB of or memory required for expiry. I mean, like memory, sorry, if I had mentioned data previously. And then created time would easily take around 2.4 terabytes. Overall, this table would need somewhere around 40.5 or 41 terabytes of storage for 300 billion rows. And this is more about the core data the database would be storing, and we'll be having some metadata and overhead storage which are required for this table, estimating it to be around 10 to 20 TB. We should be in total having approximately 65 terabytes of, or we would be needing 65 terabytes of storage for this table, mandatory table. Yeah. Now let us discuss about the optional table. If you would, please feel free to skip the optional table if you are not looking for the analytical side of it. So in the optional table, we'll keep it simple. We'll just store the short URL and the count. Over here, the count is nothing but the number of times different users have used this short URL and got redirected to the website. So given that the size will be similar for the short URL for a row, it will be 7 bytes, and the count would be of begin, and it will take around 8 bytes per row. So given that like 2.1 TB for short URL and 2.4 TB for count would be the total storage which would be and yeah, so 2.1 plus 2.4 would be 4.5 TB. This is for 300 billion rows in total. Calculating the overhead here, similarly, we'll be having around 12 TB for the second table. Yeah. Moving on, let us discuss about the design. Over here, I have came up with two different designs. The design one would be using Cassandra DB, and the design two would be using Postgres DB. For now, like let us deep dive into the design one. In the design one, when a user submits a write request or read request, it will first reach the load balancer, and load balancer would be routing the traffic to web servers that are hosted, and we will be using round robin technique, and that should be more than enough for our requirement. In round robin fashion, we'll be distributing the requests to different servers. So in the scenario one, when a user tries to generate a short URL for a given long URL, we will call it as a write process, and before a write process could start, in this approach, we have separated out the key generation into different layer, and we'll be deploying separate key generation services which will take care of generating short URL and making sure it does not have duplicate or collide with each other. To generate the short URL over here, we'll take help of ZooKeeper. Say there are like five different servers or nodes in the key generation service: one, two, and three, or four and five. The zookeeper will be responsible for sharing a limited number of um, a limited set of numbers for each node. Say node one would be getting from 1 to 1 million. It will be getting 1 million units, and the node two will be getting 1 million to 2 million. Again, it will be getting 1 million unique numbers, and node three would be getting 2 to 3 million unique numbers. So which will start from 2 million and end at 3 million. So when as and when like the zookeeper assigns the val as and when the zookeeper assigns the value to each nodes, hmm, the key generation service would basically start generating base 62 short URL suffix. And it will basically load it into the memory and keep it. At a stage, it will process all the 1 million numbers and generate 1 million unique uh, base 62 URL, base 62 short URL basically. And once this is loaded into the memory, whenever the web server requests for an unique short URL, the key generation service would fetch it from its internal memory and share it to the web servers. Over here, when the first 1 million numbers are exhausted, the zookeeper would be responsible for sharing the next set of numbers to the node. Say suppose the node 2 completes its first set of 1 million numbers. Then when the node 2 reaches out to the zookeeper will be providing third uh, the numbers from third million to fourth million, and it will not wait for the first node to come and fetch or log those numbers. So over here, we might it might seem like the zookeeper would be a single point of failure, but however, that would not be the case, because once 1 million numbers are shared into or given to the key generation service, what will happen is since it internally processes all the 1 million numbers and generates base 62 mm, strings for it. It will be loaded into its own internal memory, and it would not depend on ZooKeeper for each and every single short URL. It will be completely retrieved from its memory. So if there is any crash or a little bit of downtime in ZooKeeper, what would happen is bef- mostly the key generation service should be able to provide the unique short URL strings to the web servers from its memory with the initial given set of 1 million numbers before the ZooKeeper comes back live. So there will not be a single point of failure here. And also, when we look at the failure use cases in key generation service, since we have multiple different nodes within this cluster, uh, if any one of the node goes down, we should be having enough number of nodes to provide and support the unique base 62 strings to the web servers. Once the web servers acquires the string, uh, unique base 62 string, it will then write into the DB. So the DB write will directly happen on the uh, Cassandra DB instead of read cache, instead of Redis cache. So all these short URL, long URL, created time, and expiry time, along with other details, would be stored into Cassandra. Over here, Cassandra uses LSM. Like, however, I will discuss more in detail about LSM and SS table, and how Cassandra internally stores its data and why it is faster. And all those details will be discussed in a separate system design video. For now, let us assume the Cassandra is internally sharding its nodes and is able to manage our traffic. Yeah, it should be able to manage. Why Cassandra is fast and how it will be able to manage. Let us look into it in a different video. This is all about right. Uh, Moving on to the reads, when a user submits a read request to the load balancer would again distribute the read request across its servers in a round robin fashion, and the servers would first try to look for the Redis cache, um, and if at all, if the data is available within the cache, it will immediately respond back to the web server, and the user will be redirected to the actual website which is on the long URL. And if in case Redis cache does not have the data in it, then it will make a request to Cassandra to read the data and have a write in its memory, and then respond it back to the web server, and the user will be redirected. And over here, we'll be using LRU, least recently used eviction policy, and read through methodology um, for storing the data into cache for easier access. Let us go through some of the theory about it. Hope you understand the high level design of the approach one. Yeah, yeah. As discussed earlier, in our caching strategy, we'll be using a read through caching, wherein read through cache means when the data is not available in the cache would make a request to the actual DB, collect the data, write it in its memory, and then send as and respond back to the servers. This is called retro caching. This is one of the caching techniques which Redis uses. The next one would be the eviction policy. Say suppose the cache memory is full. Cache, the Redis would basically evict some of the data from its memory, and the technique used here would be LRU, which is least recently used eviction policy. But however, one note around this least recently used eviction policy is that in case of Redis does not have an actual least recently used eviction policy. By which I mean, it will not have all the short URLs in its memory and have a track of how much times a particular short URL has been used. That will not be captured by Redis. Instead, how the list eviction policy in Redis works is using approximated LRU algorithm, by which if it will pick 5 or 10 set of data, 10 different short URLs, and see which one is the least used among that particular set and evict the least used one. And it will iterate it across the complete memory to keep the memory to be in line with the memory policy of the cache. This is one important thing to note when if you are choosing Redis. And yeah, about Cassandra DB, when it comes to write, Cassandra would be able to achieve the high-speed ingestion using the commit logs, write-ahead logs, and mem tables within an LSM tree architecture. Yeah, let us look at this one in a separate video. It would need a separate video, and and also for the reads in Cassandra DB, instead of general indexing, it will use Bloom filters. Uh, by which it does not need to go through the entire 77 TB or like 65 TB of database, or it will not go through all 300 billion records to find the actual matching set. Yeah, let us discuss more about the Cassandra in a different video in itself. Yeah. The next thing we discussed in this design is the key generation service and the ZooKeeper layer. Let us go a little theory in around KGS and ZooKeeper. The first one would be the range allocation. When a KGS node requests a range, ZooKeeper assigns a unique block, say for example 1 million to 2 million, and ensures that the same range is never shared with another node. Yeah, once the ZooKeeper assigns the range to the node, once the ZooKeeper assigns this range to the node one, then it will never be shared again with the same node or different node in future. Say, suppose the node 1 crashes here, and it has used only 500 records out of 500 unique numbers out of the 1 million. The remaining, the whole set of remaining numbers will not be used again. And when the node 1 comes up again and asks for the range, it will be given with a new range, and the previous range would have been lost. Yeah, this is acceptable given that we have an huge amount of overhead, um, wherein like our maximum number of rows would be 300 billion for a span of 20 years, and we have an leg room of around like 2.8 trillion or 3.5 trillion in case of 62 base 62. Yeah, yeah. As I mentioned, like it will not the same set or the same block will not be shared with any other node, even the same node again. Yeah. So this is how the short URL is being generated. So the key generation service basically, as I mentioned earlier, does not each time generate the base 62 strings. Instead, when the unique block is assigned by the zookeeper, at the very initial stage itself, the node will be converting all the numbers in the unique block into base 62 strings, and it will keep it in the memory or RAM, so that when the write server makes a request to the KGS, it will immediately respond without referring to any DB or any or even ZooKeeper for that instance. It will be like very quick since it accesses it from RAM. So moving on the zero collision guarantee. So when we say collisions, no collisions would occur, or there is a zero collision guarantee, it means it is mathematically impossible to generate two same short URLs when it is being assigned with unique numbers to generate a basic C2 string. This removes the need for making additional DB calls basically. So you don't need to each time check in DB if a particular short URL exists or not. It will always be unique, and if at all, if a block is lost, it is always lost, and the same block will never be assigned to any other node. So all the strings that are generated in memory in the KGS service will always be unique. Once say suppose for the number 1 millionth one particular short URL has been generated, since it will not be shared with any other KGS nodes, um, and even with the same nodes upon failures, that particular base 64 string will never be regenerated again. So since there is no regeneration of the same base 62 string, we don't need to check if at all if any base 62 string exists in our DB or not before inserting the data. This is like one benefit we will get from having a separate KGS and ZooKeeper. Yeah, as I mentioned earlier, the fault tolerance is good. The fault tolerance, there will be no fault in the system, which means the zookeeper will not be a single point of failure. As and when zookeeper goes down, KGF will have enough preloaded keys to share it with the server before the zookeeper is operational. Yeah, this is one of the trade-off. This is where I mentioned if at all one of the KGS node goes down, only a particular set of numbers in a block would be, or only a particular set of base 62 strings will be lost. That too within the memory of the KGS node itself. There will be no writes to the DB. So this data loss is highly acceptable given that we have like more legroom or overhead. So moving on, let us now discuss about around the design too. This is wherein we'll be using the Postgres database instead of Cassandra database. Please feel free to skip this section if you're not interested in the second design, and you can move on to the optional analytical part of the video. I'll give the timestamp in the description below. Before we could discuss around the design too, let me quickly go through the DB, the DB approach we have taken here. Over here, since we'll be having around 60 terabytes of data as per our previous estimates, a single Postgres master node will not be able to take all the load for the number of writes and reads that our system is supposed to scale. So we'll be sharding the database into multiple shards, and let me show you a fair simple calculation around the shards. Yeah, over here, if you see, suppose we are sharding it into five different shards. Each of the shard will hold around 2 billion rows, and the base range for the first 2 billion would be from 0 to 2W98H6P. Similarly, from this 2W986HP to 5R FGPSA would be the second shard's range, and the third shard and fourth shard will continue so on further till like 15 shards. So given this in mind, like for a given shard we'll be potentially having around 2 billion possible entries, and for this 1 trillion is for 5 shards, say we can have 15 shards as well and make it 3 trillion. If at all, if there is an exponential scale in our systems, we might need 3 trillion rows altogether. But yeah, mm, for like our 20 years initial estimate, this 5 shard should be more than sufficient. Yeah. Coming back to the design, each of the shard will have its own master or leader. As we know, like Postgres is a single leader replication database. Shard one will have its leader and nodes within its cluster. So mostly all the writes will go to the master and the reads will happen from the slave nodes. Let me quickly show you one key important part. So in the approach one, we would have seen a separate key generation service and a ZooKeeper layer to maintain or to basically monitor and generate these short URLs. But in this approach, let us assume we will just load all 3.5 trillion possible combinations of the short URLs into the DB upfront and assign it with the value of assign it with an expiry of 0. Now, given that in mind, all the DB rows are already occupied with the or already pre-filled with the short URLs and the expiry. Now, when the read comes, when we get a write request from the server, so when we get a write request, the server will now first check and try to grab a lock on unused or an expired row. And how that would happen is uh, by this query. We will try to set the long URL and expiry um, by by these conditions, like where we will see if a particular row has been expired and it is non-zero, then we will grab a lock on that and update the long URL and expiry into that particular row. And very key important point to remember over here is to in case if we are trying to update a particular row, we should make sure that we are not trying to update a row which is locked. By which what I mean is, if there are two different write requests coming in, we might end up we might end up in a situation where both the write request will try to grab a lock for the same row and update the data. Say suppose the request one has already updated the data. The request 2, when it tries now to update the data in the same row, the data will be lost and it will be overridden. To avoid this data loss, we should make sure, like we in our short URL um, determining strategy, we should always look for a row which is not locked. And once we find the row, we should immediately grab the lock and then start updating so that there will be no collision here. This is like a very key important thing to remember. Without this, mostly the design would most likely fail when it scales to a larger extent. Yeah, update skip lot. That's how the short URL is being handled in this approach. It is a the entire available list of short URLs are like preloaded into the database with an expiry of 0, and we'll try to use the available short URLs which are not pre-used by skipping the locked ones and grabbing a lock on whichever we'll be using. And the read happens in a similar fashion compared to the design one. So when the web server receives the read request, initially it will look into Redis cache, and then if Redis cache does not have the have a particular data, then it will route the request to the Postgres DB, get the data, write it into its Redis memory, and then respond it back to the server. Let us go to some of. Moving on now, let us look at the analytical part of it. This is again optional. Feel free to skip if you're not interested in this one. This analytics part is nothing but how we store the uh, number of times a particular short URL has been used in the count table. We'll be having the short URL and the number of times it has been used in that particular table. Over here, let me grab the highlighter here. Yeah. When the request reaches the load balancer, again it will be in round robin fashion, distributed across the web servers, and web server would look into the Redis cache, and if Redis cache has the data, it will provide it back, or else like it will go to the Cassandra or Postgres DB to fetch the data and return it back. However, after the successful after we fetch the details after we fetch the data successfully, we can trigger an Kafka message in an asynchronous fashion for the analytical purpose. Upon every successful get call, a Kafka message will be published. Now, the Kafka message again, like we can use partitions to handle the huge volume in Kafka, and all these messages that are published would be consumed by a streaming layer. We can use Apache Spark or any Python file where it can process the consumed records in mini batches. Yeah, yeah, we can use either Apache Spark or a Python code to handle the mini batches. Um, so yeah, writing in DB is the little trickiest part here. We might not we should not be like basically writing each single consumed Kafka message directly by incrementing one um, in the count table. Like say for every single Kafka message, we should not go ahead and write it into the count table by incrementing the available number with one. We might end up losing some of the analytics. Say suppose there is a hotspot or a hot link which will be used by multiple different users at the same time. Say we'll then there will be thousands of Kafka messages which will be queued up for the particular hot URL, and when the DB lock has been captured for that particular hot URL, all the other writes would be waiting for that lock to be released, and there could be deadlock kind of situation happening around that particular row, and we might have failure points in this count table. To avoid that and to avoid the number of IO operations, we will use a mini batching. Will follow certain some mini batching techniques, wherein instead of a single record being written into the database or a single entry being made into the database, we will mm, have say suppose a time based mini batch or like uh, count based mini batch to update the DB. Let me just quickly go to the next slide. Yeah, over here, this is what I mean. We will aggregate the processing. So this streaming layer or the batch processing layer will track the number of times a particular URL has been hit and store it into its micro batch memory or like in code itself. And then how it would update is like it would update. So yeah, how it will not update is like it will not try to update the count by one or incrementing the count by one each for each single Kafka message. Instead, it will go for bulk updates. By which what I mean is like maybe it might get the current count and see how much number of times a particular URL has been um, accessed in the in a given batch and updated together. Current count plus say 1,000 or 100 times a particular URL has been hit. Current count plus 100 will be um, will be processed and added into the DB. This will make our systems more efficient. Yeah. This is all about how we handle the count table. Now, the last section is about how we handle the expiration policy. This could be fairly straightforward. We can have an hourly batch. So the very yeah the hourly batch can basically be an independent batch which runs for every hour or every 2 hour like or every day once and how it would what it would basically do is it will first fetch all the expired offers from the table one and fetch the short URLs of the expired offers from table one and delete the expired offers from table one and then using the captured short URLs we'll go back to the analytical table which is count table and delete the entries from there as well. This can be either achieved via Kafka or like directly via second DB query, which will delete it from the count table. This is one approach to maintain the expiration policy. Yeah, this is fairly straightforward. So let's not discuss much about this one. So yeah, that's it. We have reached to the end of the video. Thank you everyone for watching. Please do post your queries and suggestions in the comments, and please don't forget to subscribe and like this video. Thank you again, and let's catch up in the next video in this series.